Hello everyone. Today we are going to discuss a topic on eigenvalues and eigenvectors. See, here I have taken one question. It's based on Cayley Hamilton theorem. First we need to discuss about Cayley Hamilton theorem. So let's start with the statement of Cayley Hamilton theorem. So here you can see this is the statement of Cayley Hamilton theorem. Every square matrix satisfies its own characteristic equation. So first we are supposed to discuss about how do we determine characteristic equation. So let us consider a matrix A. Then we can write the characteristic equation as determinant of A minus lambda I equals to 0. So what exactly is the meaning of lambda here? See, lambda here is eigenvalue and I stands for an identity matrix. From here we are supposed to develop the characteristic equation, and from there we have to verify this statement of Cayley Hamilton theorem. So let's start it. As you can see here, A is given as 1, 0, 2, 0 minus 1, 1 and 0, 1, 0. So I am going to determine particularly this part, which is A minus lambda I. So let's find A minus lambda I. So lambda, see here, lambda is eigenvalue. So it is a specific value we have here. I stands for an identity matrix. Since this matrix is of order 3 cross 3, definitely we have to introduce this I as 1, 0, 0, 0, 1, 0, 0, 0, 1. Now let's calculate this A minus lambda I. Here you are getting 1 minus lambda, then 0, then 2, 0, then minus 1 minus lambda, 1, 0, 1 and minus of lambda. So here you are getting this value of matrix A minus lambda I. Next, our objective is to find out the determinant value of this matrix. So let's find it. Let's just expand this matrix. Since the next element is 0, so we are ignoring that part. The last one is 2 with respect to 2. Although we will get 0 here, still I am writing. So now if you wish to expand it, you will get something like this. So see, if you are just expanding this expression, you will get A minus lambda I mod. Now just multiplying. So the final expression is minus of lambda cube. We are cancelling lambda square, 2 lambda and minus 1. So this is the value of det of A minus lambda I. Now see, as per the statement of the theorem, every square matrix satisfies its own characteristic equation. We already have developed the characteristic equation, and this characteristic equation is this one. A minus lambda I mod is minus of lambda cube plus 2 lambda minus I. So we are supposed to substitute A in place of lambda. That's what we are going to do here. Now A equals to 1, 0, 2, that matrix, 0, minus 1, 0, minus 1, 1 and 0, 1, 0. This was the matrix. First we are going to determine A square. So 1, 0, 2, 0, minus 1, 1, 0, 1, 0. Simple matrix multiplication, you will get the value of A square. So let's find it. 1, then 2, 0, 2, again 0, and finally it is 1. So this is the value of a square. Since in this expression here we have lambda cube, so we are supposed to find out a cube. So let's find out a cube. So how do we get a cube? Of course, a square into a. A square into a. So I already have got the value of a. So let's just substitute the same value. This is a square and a was here. So let's calculate this once again. This is 1 minus 2 plus 2, you will get 0 here. 4, again 0, minus 3, 2, 0, 2, minus 1. So here we go, the value of a cube is becoming 104, 0 minus 3 2 and 0 2 minus 1. Next, twice of a. Let's calculate twice of a, because you see the expression is minus of lambda cube plus 2 lambda minus 1. So as I was telling you that we are supposed to substitute a in place of lambda, that is why we already have calculated a cube, and accordingly we are supposed to calculate twice of a. So let's just calculate twice of a. Twice of this matrix. So now finally we have to verify the theorem. It was there minus of a cube plus 2a, and that was minus of I. Instead of 1, since we are using it in terms of matrix, of course we are supposed to introduce an identity matrix. So minus 1, 0, minus 4, 0, 3, minus 2, then again 0, 0, 2, minus 2 and 1. This is value of minus of a cube plus twice of a. Twice of a is 2, 0, 4, 0, minus 2, 2, 0, 2, 0 and minus of I. This time 1, 0, 0, 0, 1, 0, 0, 0, 1. So see, minus 1, minus 1, minus 1. It is coming as minus 2 plus 2. Here it is 0. Then again 0. Again it is 0. Same goes for the second row. Look at the second row. It is all 0, all the elements. And same for the third row. So it is 0. So look at this. Here we started with the characteristic equation a minus lambda I, the determinant of a minus lambda I, and accordingly we developed this equation. This was the characteristic equation. Finally, when we are substituting a in place of this lambda, we are getting the value of this expression as 0. Hence, the characteristic equation is satisfied by the given matrix. Hence, this Cayley Hamilton theorem is verified. Thank you.